And thank you all for coming again. And for today, I will record something, review something we have done in the previous lectures, and then I will introduce the notion of Butler permutations, and then I will prove the very important proposition, which almost completes the proof of our combinatorial formula for the McDonald intersection polynomial of two partitions. Okay, so let me first review this one. So starting from this partition mu and lambda, which is very similar looking. So one can be obtained from the other by moving a cell. Then we applied some column exchange rule and cycling in an appropriate way. And finer field diagrams, these two are like almost identical. So they are identical except for the two columns in the right. And our goal today is to analyze these two columns. Okay, so that's to analyze those columns, I have to introduce Butler permutations. Okay. So to define Butler permutation, we have to consider directed perfect matching. So we will consider directed perfect matchings. And I have to define some notions, but I will just give you an example of directed perfect matching and define notion in that example. So as you know, perfect matching is given by arcs connecting two dots. And so 1, 0, 1, 2, 3, 4, 5, 6, 7. And we will connect two dots by an arc, but in this time we give a direction for each arc. So 0, 2, 1, 5, 6, 7, 4, 3. And of course, we can name an arc like alpha 1, alpha 2, alpha 3, and alpha 4. Sometimes we can display our perfect matching in this way, or we just use 0, 2 to represent this arc. So this arc goes from 0 to 2, okay? So 0, 2, 1, 5, 4, 3, and 6, 7. And we say on arc, like alpha 1, alpha 3, alpha 4 is in forward direction. If the directed arc is I comma j and I is less than j. So alpha 1, alpha 1, alpha 2, and alpha 4 are in forward direction. And the remaining arc, alpha 3, is in reverse direction. So it's 4 comma 3 and 4 is bigger than 3, so it's reverse direction. And as usual, we'll say alpha 1 and alpha 2 is crossing. Like if you have this shape, or the indices of alpha 1 and alpha 2 are kind of interlacing, then we will say that alpha 1 and alpha 2 is crossing. And if not, we say that those are non-crossing. So for example, alpha 2 and alpha 4, they are non-crossing. It's non-crossing. And of course, alpha 2 and alpha 3 are this is non-crossing, but we will say that alpha 3, it is non-crossing, and we will say that alpha 3 is nested by alpha 2. So alpha 3 is kind of inside the arc alpha 2, so we will say alpha 3 is nested by alpha 2. And for from these notions, we can define the Butler permutations. For a permutation W, we will consider a directed perfect matching. M of W, which consists of alpha 1 of W to alpha large N of W, and this large N is 2 over N plus 1 if N is even, and otherwise, so if N is odd, the large N is N plus 1 over 2, okay? And this directed perfect matching is on the vertices 0, 1, 2, and minus 1, and whose arcs are defined by, so starting from the last arc, alpha large N. So alpha large N of W is 0, W1, okay? And alpha N minus 1 of W is W1, W2, W3, okay? So, and in general, alpha N minus I of W is W2I, W2I plus 1 for I starting from 0 to N minus 1. And where we regarded W0 is 0 and W2 and WN plus 1 is N plus 1. Okay. So I will give you an example. So let's consider M of 2, 4, 1, 3. Okay. So you always take this 0 here and 5 here if N is even. So you put 0 and N plus 1 and connect 0, 2. So, okay. And connect 0 and 2 to get the last arc, alpha 3. And connect 4 and 1 to obtain alpha 2, and 3 and 5 will give alpha 1, okay? And for another example, where N is odd, so for example, the permutation is 3, 1, 2, 4, 5. You put this 0 here and connect all these pairs. So 0, 3, 1, 2, and 4, 5, and name them alpha 2, 3, alpha 2, alpha 1. Okay, so these are the matching, directed perfect matching associated to a permutation. And then
just a silly comment here. On your previous page, just a notation for everyone. Capital N, I know you divided it into two definitions generously, but you can write it compactly as ceiling of N plus 1 over 2.
Oh, yeah, that would be nicer. So like this. Oh, N plus 1?
N plus 1.
Okay, yeah.
Not the floor, but the ceiling.
Oh, ceiling, okay. Okay, thank you for the comment.
Thank you.
Yeah, we defined the perfect matching associated to permutation, and and let KW be the smallest integer among M, so where M satisfies that alpha M of W and alpha M plus 1 of W, so these are pair of arc. This is non-crossing. Of course, it can happen that all these pairs are crossing, so if exist, and I will deal with that situation later. So if exist, let k be the smallest integer. So alpha 1, alpha 2 is a crossing, alpha 2, alpha 3 is a crossing, and so on. And alpha k minus 1, alpha k is crossing, but alpha k and alpha k plus 1 is non-crossing. And for this situation, we say a permutation W is a Butler permutation if either one of these two conditions satisfied. So alpha k plus 1 of W is nested by alpha k W, and alpha k W is in reverse direction. Or alpha k plus 1 W is not nested by alpha k, and alpha k W is in forward direction. Okay. And as I said, it is possible to it is possible that there is no such k. So if there is no such k, then we say W is a Butler permutation for this case. If alpha, the almost last arc, so alpha n minus 1 of W is in reverse direction. Okay. And we will denote the set of Butler permutations. Set of Butler permutations by curly Bn. Okay. And I will give you an example. So first example comes from this one. So for example, alpha in this example, alpha 1, alpha 2 is a crossing, alpha 2, alpha 3 is a crossing. So this is the case that there is no such k. So in this case, alpha n minus 1, which is, alpha 2 is in, so it is in, alpha 2 is in reverse, alpha 2 is in reverse direction. So our permutation 2, 4, 1, 3 is a Butler permutation. And for another example, M of 3, 2, 1, 4. So we have to draw perfect matching. Consider 0 and 5 here, and connect 0, 3, 2, 1, 4, 5, like this. 2, 1, 4, 5. And since, and alpha 1, alpha 2, alpha 3. Since alpha 1 and alpha 2 forms, they are non-crossing, so our k is 1, and alpha 2, alpha k plus 1 is not nested by alpha 1, alpha k, okay? And alpha 1 is in forward direction. So this fits in the second condition here. So alpha k plus 1 is not nested by alpha k, and alpha k is in forward direction. So this will conclude that the permutation 3214 is a Butler permutation. Okay. And finally, I will give a non-example, 1, 4, 2, 3. Okay. And you put 0 and 5 here, and connect 0, 1, 4, 2, 3, 5, alpha 1, alpha 2, alpha 3, and alpha 1, alpha 2 is crossing, alpha 2, alpha 3 is non-crossing, so our K is 2 in this case. And once again, alpha 3 is not nested by alpha 2. But here, alpha 2 is in reverse direction. So this concludes that the permutation 1, 4, 3, 5 is not in a Butler permutation. It's not a Butler permutation. Okay. And easy observation you could make is that
do you mean
yes.
1, 4, 2, 3?
Oh, sorry. Sorry. 1, 4, 2, 3. Okay, thank you. And an easy observation you could make is that the membership of a Butler permutation or not is determined by some arc is in reverse or forward direction. And that will give the Butler permutation is half of the OR permutation. So the number of Butler permutation is n factorial over 2. And our goal was to write down the combinatorial formula for McDonald intersection polynomial as a generating function of step times fundamental quasi-symmetric function over Butler permutation. So this fact kind of compatible with the n factorial over 2 conjecture. And moreover, we can observe that if we sum the inverse descent W over all Butler permutation Bn, then it will give H2 1 1 1 1 1 1. Okay. And this proof is very nice. So I want to introduce the proof. So let's define. Yeah.
In your last comment where you have half of the size of permutation, like the size of alternating group, do you have a similar construction of sort of permutations for n factorial over k?
No, that's the problem. I mean, of course we can somehow. If you want a permutation, a set of permutations that has size of n factorial over 3, there's multiple way to define that, right? I mean, you can, yeah, but that we have very many choices, but this one, so for example, if you want a permutation like n factorial over 3, so let's say xn, then the sum of these inverse descent W should be H2 2 1 1 1 1 1 minus, 2 times minus H3 1 1 1 1 1. Okay. And we don't know a natural way to define this set xn. And of course, for n factorial over k, we don't have. So we don't have a candidate for n factorial over k.
Okay, thank you.
Yeah, thank you for the question. And okay, let's prove this one. So the proof goes like, so Sn prime, let's define Sn prime to be, so we divide the permutation, the set of permutation into two subsets. So the first one is a set of permutation where first 2 arc is non-crossing. And the second one, so we want partition, so the first 2 arc is crossing, okay? And define Bn prime by Bn intersection with Sn prime, Bn double prime is Bn intersection with Sn double prime. So we kind of partition our Butler permutation into 2 sets. And for the first case, so if W is Bn plus 2 prime, it is easy to see that since since alpha 1 and alpha 2 is non-crossing, our K is 1. So to see if our permutation is Butler or not, all you have to do is see the alpha 1 and alpha 2. So you don't have to worry about the things in the front. So this is Butler permutation if the standardization of the permutation restricted to the last n positions are in Butler permutation. And once again, since the arc A alpha 1 and alpha 2 is non-crossing, that condition holds for this standardization. Okay, and since this condition, we don't have any conditions for the first two letters. So if you sum f of inverse descent of all permutation Bn plus 2 prime, that what you obtain is sum of Bn prime f inverse descent of W. And since you don't have any condition on the first two letters, so the left-hand side is obtained from right-hand side by multiplying H11. Okay. And for the second part, we define a map flip Bn double prime to Bn double prime to Sn double prime minus Bn double prime by reversing the direction of the arc alpha k of W. So since we reverse the direction of alpha k, the crossing condition does not change, but the membership in the Butler or not changes because we reverse the direction of the critical arc. And one more thing we can observe is that alpha k and alpha k minus 1, this pair is crossing because k is the minimal integer that alpha k and alpha k plus 1 is non-crossing. And since we start from alpha 1 and alpha 2 is crossing, so there's k minus 1 here. And you see that these indices of alpha k has some index between these two. So for example, like 3 and 5, so it's 4. So if you swap 3 and 5, the inverse descent does not change because we have 4 in 4 is not between them. So what I have said is like we have inverse descent of W is equal to inverse descent of flip of W. Because this happens. Okay. So by these observations, we can say that the generating function of f inverse descent of W of all permutations in Bn plus 2 double prime is half of all permutation in Sn plus 2 double prime. And this, since there is no condition for this one, so there's no condition for this one, so we can somehow say that this is WSN plus 2 double prime Sn double prime f inverse descent and H11. Okay, since there is no condition for the first two letters. And by these observations above, this equals to the Bn double prime, the generating function of f inverse descent over all permutations in Bn double prime times H11. So if we sum these two equations, what we obtain is sum of Butler permutation plus 2 f inverse descent W is sum of all Butler permutation Bn of F inverse descent W times H11. Okay? And this essentially proves the induction part. And if you write down all Butler permutation of size 2 and 3, what you will obtain is H2 and H21. So those are the initial conditions, and this is the induction process. Okay, so that's how we prove this proposition. And yeah, once again, I will record this. So
somehow you get some sort of recurrence.
Yeah, between this sum of F inverse descent of Butler permutations. Yeah. And recall that we started from some partitions or its standard filling. And we applied column exchange rule and cycling to obtain these new fill diagrams, which are identical except for the two columns. And we are about to analyze these two columns. So what are these two columns? So these are the shape are like this. So there is one box here. I mean, one box is excluded here.
Excuse me, sorry. If you don't mind, go back to the statement of the theorem. The proposition, yeah. In your argument, what shows me at the bottom is this recurrence with H11. You can repeatedly go on. So compared to the theorem that you have, the proposition statement, it accounts for all the ones. Where does the 2 come from in the H?
Oh, so if you the initial case, so the initial case is B2 F inverse descent. I just said it, so yeah, I should have written that. So the initial conditions are like this: B3 F inverse descent W is H21. And these initial conditions can be proved by writing all the Butler permutations of 2 and 3. And starting from this, you multiply by H11, so you can prove the proposition.
Yeah, that helps me. Thank you.
Yeah, and we go back to analyze these two. So the second diagram is of shape this, and the first diagram is something like this. And the height are the same, okay? And in the second column, the first row is excluded. And you can see that this filling is the same as this filling. I mean, it's not enough. I mean, it's too short to observe that, but yeah, this one is the same as this one. And if we let this one to be alpha, then this one is Q times alpha. So it's Q alpha here. And again, it's two small examples, but you can obtain this this Q minus 3T3 by multiplying alpha to this one. So it's alpha y here and y here, okay? And you do the same computations for many examples of pair of partitions, then what you can obtain is this one. So this is proposition 4.14 in our paper. And let's say we have a field diagram mu f mu like this one. So the first, top rows, the fillings are kind of arbitrary, and you have Q alpha here, and the filling of the first column is obtained from the second column by multiplying alpha. Okay. And suppose you have a second fill diagram. You kind of exchange these two columns, but leave the first row in its position, and you divide by Q. And since you have to have filling here and you don't have to have filling here, you raise this one and put alpha a n minus 1. And let's say this is a field diagram, lambda f lambda. And we say we will denote the conditions for these two field diagram as double star. Okay, and this is quite similar to this column exchange rule situation. We had two field diagrams, and we denote the condition by star. Okay, and this is another condition. And proposition 4.14 claims that there exists a bijection. So we need another bijection, which I will denote by zeta n comma m of permutation of size n plus m minus 1, which is the number of cells in a diagram here. So this is n, and this is m minus 1. Okay. We want a bijection zeta satisfying three conditions. So zeta 1, zeta 2, and zeta 3, and zeta 2 and zeta 3 are easy. So inverse descent of W. So inverse descent is preserved. So inverse descent of zeta, image of W. And I'll just say zeta is content preserving, as always. And the first condition, so we are trying to calculate the McDonald intersection polynomial, and in this case we are trying to calculate this one. So McDonald intersection polynomial of mu minus alpha times McDonald intersection polynomial of lambda divided by 1 minus alpha. And we want the result we want is write this symmetric function as a generating function of stat of W times f inverse descent of W over permutations of Sn plus n minus 1, where if it is restricted to the from n minus m position to the last position, its standardization is a Butler permutation of size 2m. So this restriction, so it's here. Okay. Okay, so I'll just color it green. Okay. So to obtain this, we have to divide our cases. So if this one is Butler permutation or not. Okay. So if it is a Butler permutation, the stat is preserved. Okay. Stat mu f of W is stat lambda of image of W. Okay. So because stat is preserved, so these are the same. So if you calculate this x minus alpha x over 1 minus alpha, it will give x. So here we have x. Okay. And if this is not a Butler permutation, then the stat is obtained by the stat lambda, f lambda of image of zeta times alpha. So for some terms, you have alpha x here, and we alpha times x here. So alpha x minus alpha x is 0. So all the term that this restriction is not a Butler permutation vanishes. So that's how we prove this. Okay. So if there's such a bijection zeta, we can prove this. And as we did in the column exchange rule, since our bijection zeta is content preserving. This is local. So by local, what I mean is, we not only we can analyze these two column shape, we can also analyze if you have two field diagrams which are identical except for two columns, and those two columns, if they satisfies the condition double star, then we can analyze the same thing like this one for those two field diagrams, the whole field diagrams. So that is the consequence of this proposition 4.14. And I will sketch the proof of this proposition. So first of all, okay, starting from this field diagram, we may focus, because the zeta is content preserving, the zeta for these parts should be identity, and the stat are kind of obvious. So we can erase these first top rows and obtain these field diagrams. Okay. And this is M. Okay. So, and let me denote this field diagram by, I'll use N. And mu bar of N. Okay, so it's lambda bar of N. Okay, and we want a bijection connect zeta N, which connects these two. And if you remember, this one, and in the proof, sorry, where is the proof? Okay, this one. So we have defined field diagrams mu N and lambda N. Okay, and if you carefully see this, the field diagram excluding this first cell, the cell in the bottom, this is equal to mu n minus 1 f mu n minus 1. Okay, and once again, starting from the second field diagram, and if you exclude the first row, then what you obtain is lambda n minus 1 f lambda n minus 1. And we know how to deal with this stat mu n minus 1 or stat lambda n minus 1, so we could proceed by induction. So what I'm saying is stat mu bar of a permutation W is given by stat mu n minus 1 of W, of course restricted this to first to n minus 1 position. And then the additional stats are, we can have at most one inversion here, and we can have at most one descent here. So it's the additional stats are Q if W to n minus 1 is bigger than W to n, and alpha A n minus 1 if W to n minus 2 is bigger than W to n. Okay, and likewise, we can write stat lambda bar as stat lambda n minus 1 times at most one inversion and at most one descent. So in this time, we have a n minus 1. Okay, and what we are trying to do is compare these two. And if you see this stat and this stat is kind of related with the map phi n minus 1, which we have used to prove the column exchange rule. So once again, we write down the additional stats or the ratio of this one and this one for each permutations. And to calculate this additional stat, what we really have to care is the last three words, last three letters. W2n minus 2, W2n minus 1, and W2n. And actually, we just need standardization. So we have 6 permutations like this. And we can divide this into 3 parts because our zeta need to be content preserving. And if you see this, a few things you can observe is that if you have permutation that ends like this, then these should be Butler permutation because so the first arc, so it's 1, 2, 3, 4, and first arc is 3, 4. I mean it's n plus 1, and 1, 2, 3 is kind of relative position, but yeah, this is alpha 1, and we don't know the direction, but this is alpha 2. And alpha 2, I mean, our k is 1, and alpha k plus 1. So alpha 2 is not nested by alpha 1, and alpha 1 is in forward direction. So any permutation that ends with this pattern, it is Butler permutation. And conversely, these two is not Butler permutation. And you can see the nice pattern here. So if this is a Butler permutation, the additional states are the same. I mean, if for these pairs, the additional states are the same. And for these pair, which were not a Butler permutation, the additional states are multiplied by alpha. So this is what we have wanted. So we can send this stat in the denominator to the stat here in the denominator by the map Bn minus 1. So we can pair these up and send construct the map zeta using the map Vn minus 1. Then we can obtain the desired zeta. But you cannot do the same thing for these two. I mean, for these two, it's not determined yet if this is Butler permutation. So because 1, 3, 2 is like this. So 2, 4, and 1, 3. So it's alpha 1 and alpha 2. And since alpha 1 and alpha 2 is crossing, so we cannot tell before we see alpha 3, alpha 4, and so on. Okay, so it's not determined if it is Butler or not. And the stats are kind of weird. So these two are equal, but these two are, the first one is obtained by multiplying alpha. So to deal with this situation, we had to define, yeah, we are constructing lots of bijections. So we had to define eta 1 and eta 2 for this situation. So, and eta kind of, these are the bijection for the permutation in the front, so excluding the last one. And eta 1 is the bijection for the last letter. So 3 is bigger than the 1 just before. So 3 is bigger than 1. And eta 2 is defined in the reverse inequality situation. So last one is less than the one just before. And yeah, and these are the...
And then,
yeah.
are this useful? Are this useful for dealing with the inverse descent, these new mappings?
Oh, so yeah. If I'm understanding correctly, you're asking this eta 2, right?
Eta, yeah, the etas that you introduced, are they gonna preserve some kind of descent?
Yeah. This is the lemma for eta 1 and eta 2. So if you see this, we want our bijection eta 1 and eta 2 for such permutations. So the permutation who has condition on the last 2 letters. And eta 1 and eta 2 kind of, sometimes they preserve the stat, sometimes we have to multiply alpha. And inverse descent is preserved for both eta 1 and eta 2, and content is preserved by both eta 1 and eta 2. Okay. And to prove this, we use the similar argument once again. So to construct eta 1 and eta 2, we proceed by induction and we write down all the additional stats, and we can observe that eta 1 and eta 2 can be constructed using the maps just before. So eta 1 n minus 1, eta 2 n minus 1, phi n minus 1, and psi n minus 1. And phi and psi were defined in the proof of the column exchange rule. So we need all the bijections to construct eta 1 and eta 2. And finally, so to prove the proof of proposition 4.14, so we have to construct the bijection zeta, and we construct zeta n using eta 1 n minus 1, eta 2 n minus 1, and phi n minus 1. So like this picture. So for some cases we use phi n minus 1, and for some cases we use eta 1 or eta 2. And yeah, we have to take care of all cases and check if inverse descent preserving part or stats are correct, but that's very typical, and that makes our paper long enough. So, but all those are kind of typical to prove. Okay. And from now on, I will finalize the proof of our combinatorial formula. So once again, I will start with this example. So suppose we have two partitions, lambda and mu of these shapes. So they are identical except for two columns, and those two columns, they are different by a cell. So one can be obtained from other by moving a cell from one column to other column. Okay, and we apply column exchange rule like in this way. And our lemma 5.2 asserts that the condition star, which we need to apply the column exchange rule, it holds while applying column exchange rule. Okay, I will skip the proof, but lemma 5.2 is asserts this one. And I will apply column exchange rule. So move this first column all the way to the left, move this red column all the way to the right. And yeah, I'll just make it pretty. Okay. And move this, for this case, move this second column all the way to the right, move this red column all the way to the left. And yeah, place it like this. And we apply cycling to move the first column all the way to the right, but we have to place it one row up. So for example, we move this column all the way to the right, but place it one row up. Okay. Do the same thing for this one. And lemma 5.3 asserts that, so if you see this shaded region, the shape is obviously the same because we started from those kind of shapes. But moreover, what we obtain is the filling function of these shaded regions are the same. Okay. So as we have seen in the previous examples, and these two purple regions, in addition, the purple regions satisfies the condition double star, where we have dealt with in the proposition 4.14 here. Okay, so that's why we can apply proposition 4.14. And finally, if you define the Butler permutations of lambda and mu by a permutation where the restriction, the standardization and the restriction to d prime, where d prime is this one. So I'll just color it green. Is Butler permutation of 2m, where the height of this red column was m. Okay, and let me denote the field diagram here as df and define stat lambda mu. Oh, okay. And then what we obtain by proposition 4.14 or all the lemma 5.2 and 5.3 and column exchange rule is our the McDonald intersection polynomial of lambda and q, which was defined by t lambda h tilde mu minus t mu h tilde lambda t lambda minus t mu is given by the generating function of stat ef of w times f of inverse descent of w, where w is over all Butler permutations of lambda and mu. And yeah, and this completes the proof. And I would like to highlight some consequences. So you have now we have a fundamental posisymmetric expansion for the McDonald intersection polynomial I lambda mu, and from that our stat preserves well under the standardization, so we can convert that formula, the fundamental posisymmetric expansion, to the monomial expansion. So we have to define b lambda mu rho, which is the set of weight rho words whose standardization is Butler permutations. And we can write the monomial expansion as a generating function over those Butler words or something. Okay. And the second thing I want to highlight is that the McDonald intersection polynomial at q and t equals to 1 will give this h, very nice h expansion. And the proof is almost done in the proposition that I gave here when we were talking about the properties of Butler permutation. So this proposition is almost the proof of this corollary here. Okay. And these are all I have for today, and I'll just mention a few things for the next lectures. And in next week, in the first lecture, I mean fifth lecture, I will review some backgrounds or LLT polynomials, LLT equivalence, and I will recall the sure positivity of LLT polynomials. And using that sure positivity of LLT polynomials, we could prove some partial cases for Butler's conjecture. So I will show you how to prove that those partial results. And in this last lecture, I'm not sure the last lecture is long enough. I mean, I can do it like 30 minutes or something, right? I can shorten it. Okay, so the last lecture will be short, and in the last lecture, I will introduce some combinatorial formula for Qt Koska polynomial, which is compatible with Butler's conjecture. For the case mu is hook, or mu is a 2 column, or 2 row. Okay, so and I will discuss some progress that Alexander Vetter is making, and that's all for next week, and thank you for listening. Next up.
Thank you so much. Any questions?
This is perhaps a silly question because the word flip is like so flexible. But in your proof of the sort of the first proposition is the flip map that you defined. Like, is there any sort of relationship to the Bergeron Garcia flip map from like their science fiction paper?
Okay, so flip is defined here. So
yeah,
I'm not sure. I mean, I think not, because I mean, the flip in science fiction conjecture is it has to take QT reverser and omega, right? So the omega involution for the fundamental quasi-symmetric function should change the index, but in here the flip preserves the inverse distance. So, but in a sense, I mean, to prove the science fiction conjecture, we should find some kind of flip operation, right, to the permutations, and flip should change the membership of the Butler permutation. So in that sense, this is similar to that, but for the other reasons, so it's not the desired one. Thank you for the question.
Thank you. Thank you.
Any other questions? Actually, I have one. So the Butler permutation, like, do you have, or like, I understand that you define it because of solving this problem, and that's why it's called Butler permutation. But is there any other like combinatorial properties that's interesting from this type of permutation, or anything like, like in permutation, we have a lot of things that we can do with them, right? Like, for example, like you can have all sorts of different things on permutation, right? You can have some sort of like decomposition of that. Like you can do pipe dreams, you can have different diagrams. So if you use these traditional or classical tools on these specific permutation, is there anything interesting that you know?
Yeah, the answer might be no, and we haven't explored those direction, but I think it should be interesting. I mean, we haven't thought of it. We haven't done anything. Like, yeah, for example, we can make generating functions over number of descent or something, but we haven't done
so I was just wondering. Okay.
And one thing I want to remark is that, I mean, this Butler permutation is related to the McDonald intersection polynomial of two partitions. So if you want to get further, you have to make the permutations that involves, I mean, 3 columns. And we believe there should be a way to analyze it. And we believe that this is very hard problem, but if there's such a set of permutations, I personally believe we should have this kind of characterization. So we have paired the indices, but maybe we have to take care of triple of indices and see if they are crossing, or see their conditions, how they are placed, and that's the vague idea, but we found that problem very hard. Yeah.
Thank you. Any other questions? All right, if not, that let's finish this speaker again. Thank you.
Thank you for listening.
So I will see everyone next week.
Yep. Thank you. Bye-bye.